Hi everyone, welcome to Elecom Edu. This is our next session. Till last session, you studied what is PN junction diode and what is the unbiased condition of PN junction diode. Okay, so by this class, we are going to learn on two types of biasing. One is a forward bias, and another one it is a reverse bias. I hope you remember what and all we studied there in our last class, right? Okay. So, if you consider the diode, it is of dielectrorod, right? Means that it is having two electrorod. One electrorod is cathode and another one electrorod is anode. If you want to fabricate a diode, you are in need of two semiconductor. One is a p-type semiconductor and another one it is a n-type semiconductor. So remember all those things and please follow, right? Consider this is a silicon. It may be silicon, otherwise it may be germanium. Okay. So to this silicon or to this germanium, I am going to add a p-type semiconductor. Otherwise, I am going to design it as a p-type semiconductor. Otherwise, I am going to design it as a n-type semiconductor. So, if I want to fabricate it as a p-type semiconductor, I am in need of trivalent impurities. If I want to fabricate it as a n-type semiconductor, I am in need of pentavalent impurity. So, to this silicon, I am adding trivalent impurity. To the germanium, I am adding pentavalent impurity. So, if the silicon gets added with the trivalent impurity, the resultant is p-type semiconductor, and the semiconductor which is getting added with the pentavalent impurity, it will become the n-type semiconductor. And two more things I hope you remember. Here we used to call it as a donor. Here we used to call it as a acceptor. Okay. So now based on this we are going to fabricate this. Okay. So consider this is your p-type semiconductor. Consider this is your n-type semiconductor. Right. So how you fabricate the p-type semiconductor? By adding trivalent impurity to the pure silicon, I mean the intrinsic semiconductor. So how can we fabricate the n-type semiconductor? By adding pentavalent impurity to the purest form of silicon. So in a way, I designed a diode. So the diode is getting fabricated. So after that what we have to do? We have to take two metal leads from both sides. So I have taken one metal lead from the p-type semiconductor and one more metal lead from the n-type semiconductor. Okay? Right. So now this is a p-type semiconductor and this is your n-type semiconductor. Right? Okay. So in the p-type semiconductor, holes are the majority charge carrier and electrons are the minority charge carrier. In n-type semiconductor, where electrons are the majority charge carrier and holes are the minority charge carrier. The holes I am showing by the circle, but holes are the majority charge carrier. So means that the number of holes are more. So the number of holes are more. Okay, so holes are the majority charge carrier and electrons are the minority charge carriers. So some electrons are available. Here the electrons I am making by the dash. Here electrons are the majority charge carrier. See, these are the electrons. Electrons are the majority charge carrier and holes are the minority charge carriers. Right? So this is a place we used to call it as a junction. It is a place where the p-type semiconductor and n-type semiconductor meet each other. Okay, it is a place where it is joined together. Okay, right. So P, this terminal used to call it as a anode, N terminal we used to call it as a cathode, right? Okay, so now check, here there is no application of external voltage, I mean no biasing. That's why we used to call it as a unbiased semiconductor. Okay, so unbiased PN junction diode. Okay, you want to know what is mean by bias. So what is a bias? It is the application of external voltage. We are going to apply some voltage to this particular diode, that is termed as a bias. So there are actually two types of biasing. One is a forward biasing and another one it is a reverse biasing, right? So forward bias. So what is forward bias? P-type semiconductor gets connected with the positive terminal of the battery and a N-type semiconductor gets connected with the negative terminal of the battery. So that is called as a forward bias, right? So if it is a reverse bias, P-type semiconductor gets connected with the negative terminal of the battery and the N-type semiconductor gets connected with the positive terminal of the battery. Okay, so whenever you are considering any batteries, it is having both the positive terminal as well as negative terminal. Okay, right. So first I am going to consider a forward bias. Okay, right. So this is your unbiased condition. So Pn is unbiased. Okay, now see, it is a positive terminal of the battery, this is a negative terminal of the battery, positive terminal of the battery and a negative terminal of the battery. So what is a forward bias? P-type semiconductor gets connected with the positive terminal of the battery and the N-type semiconductor gets connected with the negative terminal of the battery. So this is termed as a forward bias. So forward bias, that's why I am mentioning it as a VF. So what is this V represents? It is a voltage. What is this F represents? Forward. So I am considering it as a forward voltage. Okay, right. So P is getting connected to positive terminal of the battery and N is getting connected to the negative terminal of the battery. Okay, right. Okay. See, already I said about this circle. So what is this circle represents? Those are the holes, because P side where holes are the majority charge carrier. What is this represents? This represents electrons. So what is that electrons? Which are the minority charge carrier. And remember, here it is having the acceptor ion, right? Because how you fabricated your P-type semiconductor? Because of the trivalent impurity. So what is the trivalent impurity? Those are the acceptor ions. So what is the extra thing available there? Which is your acceptor ion. Okay. Next, come to this N-type semiconductor. In the N-type semiconductor, this represents the electron, the negative sign which represents the electron, and the circle which represents the hole. Again, electrons are the majority charge carrier and holes are the minority charge carrier, right? And what kind of ion will be available here? Those ion are the donor ion, right? So it is having one more part, that is a donor ion. Okay, right? Okay. So now I hope you remember the depletion region, right? Okay. So in the unbiased PN junction, what is actually happening? So just to consider, you are not at all applying any voltages, right? So this is a P and N. You are not at all applying any voltages. So at that time, what will happen? P, where holes are the majority charge carrier, and N, where electrons are the majority charge carrier, right? Means that the gradient concentration, the concentration gradient of holes is in p-type and concentration gradient of electrons is in n side. So means that p side have only less number of electrons and n side have less number of holes. So means that this is in the unequilibrium condition. So to make that as a equilibrium condition, what will happen? These holes try to move from its own region, I mean from the p-type semiconductor to n-type semiconductor, where the number of holes is less. At the same time, what these electrons will do? The electrons will move from the n-type semiconductor to the p-type semiconductor because the number of electrons in the p-type semiconductor is less. Okay, right. So once the charge carriers are moving from one place to another place, we used to call it as a current, right? But what kind of charge carriers are moving? Majority charge carriers are moving, right? In the p side, where holes are the majority charge carrier, which is moving from right side to left side, right? So what is moving? The holes, which are the majority charge carrier, moving from right side to the left side. So at the same time, what electrons will do? It also will move from this region to this region. So remember, whenever the majority charge carriers are moving from one end to another end, so the current produced, which is termed as a diffusion current. Okay, right. So at the same time, the minority charge carriers also can move from one place to another place. If the minority charge carriers are moving, we used to call it as a drift current, right? Okay, now see, the holes are moving from p region to n region and the electrons are moving from n region to p region. So remember, here electrons are moving from this region to the next region. So means that it is losing the electron. So what is happening? It is losing the electron. So if the electrons are getting loosed, if it is missing the electrons, so automatically the ion will be produced, right? So if the electrons are missing, if the electrons are moving, so automatically positive ions will be produced here. So what will happen? The positive ions will be getting accumulated near the junction. Okay. At the same time, check here. Here what is happening? The holes are moving, right? So what is the holes? Holes are the positively charged particle. It is losing the holes. If the holes are losing, so what will happen? The negative ion will be produced. So the negative ion will be produced near the junction, right? See, this is a place, it is accumulated only with the ions. So these ions are actually immobile, means that it can't able to move from one place to another place. So this is actually depleted of charge carrier. So their charge carrier is getting depleted. So that's why we used to call that region as a depletion region. Okay, right? Okay, so now see, I am applying a positive voltage to p-type semiconductor and I am applying negative voltage to the n-type semiconductor. See, here which are the majority charge carrier? Holes are the majority charge carrier. So what kind of charge I am applying? Positive charge I am applying. See, holes are the positively charged particle and the applied voltage is also the positive voltage. So what will happen? Like, it's a like charge, right? So like charges repel each other. So if the like charges are repelling each other, so what will do? The holes are trying to move from the p region to the n region. Otherwise, the holes are trying to cross the junction, right? So what the holes will do? The holes are trying to cross the junction, right? Because of the application of positive voltage, the holes available in the P region trying to reach near the junction, right? The same will be happened in your N side also. In the N side, which are the majority charge carrier? Electrons are the majority charge carrier. What is this electron? Which is a negatively charged particle. So what kind of voltage we are applying? Negative voltage we are applying. Again, what is happening? It's a ripple. It's a ripple will happening because both are the like. So at that time, what this electron will do? The electron gets repelled by the applied negative voltage and it also trying to move from its own place to the junction, right? Okay. So what is there in the junction? The junction which is having a positive ion in the N type, which is having the negative ion in the P type, right? So which is approaching to the junction, I mean to the depletion region, holes are approaching. So what is there in the depletion region? Some ions are there. Again, come to this P type region. In the P type region, holes are the positively charged particle getting repelled by the application of positive voltage and it tries to reach to the junction. Near the junction, in the depletion region, there is having a negative ions. So what will happen? Holes are the positive charged, the available ion or the negative charge. So what will happen? Positive and negative will recombine. So once it is getting recombined, so what will happen? It will become the null charge, right? Consider the same in your N-type region. In N-type region, because of the application of this negative voltage, this electrons getting repelled by this negative voltage and it tries to reach to the junction. So there near the junction there is a depletion region. That depletion region is of positive ion. So the approaching one is a negatively charged electron. The available one is a positively charged ion. So again what will happen? Some recombination will be happen. So that's why the depletion region width will be reduced there in the forward bias. In the unbiased condition, the depletion region will be more or less, okay? But once if you are applying the forward bias, so what will happen? The width of the depletion region will be getting reduced. So what about the width? So width of the depletion region is getting reduced because of the application of VF. So once you are increasing your VF, so automatically the width of the depletion region is getting reduced, right? Okay. So now which is actually moving? The positive, I mean majority charge carriers are moving, right? So if the majority charge, okay, so the holes are moving from the P side to N side. So what are the holes? Holes are the majority charge carrier. Then what kind of current is producing there? Diffusion current is producing there, okay, right? That's why this current is termed as a majority current, okay, right? So remember in the forward bias, what will happen to the depletion region width? The depletion region width will be getting reduced. Once we are increasing the forward bias, automatically the depletion region width will be decreased, okay? I'm increasing more, right? Even I am increasing the forward voltage. So what will happen? All the holes or the electrons will be recombined with the available ions near the junction and after some particular time period there will be the flood of electrons from the N type towards the P type. So some flood of electrons from the P type to N type. So at that time the current will be increasing exponentially. The current will be increasing exponentially, okay? So I is equals to exponential current. So I is the exponential current. Why that exponential current is happening? Because I am increasing my forward voltage. So once I am increasing my forward voltage, the depletion region will be reduced. So after some particular time period, there will be more number of electrons flowing from N type towards P type. You know why? Because the depletion region, it was completely erased, right? Okay, so now what is only there? Junction is there. So what is the applied voltage here? Positive voltage. What is the applied voltage here? Negative voltage. Which are the majority charge will be getting absorbed by the positive terminal of the battery. So the current will be increasing exponentially once the barrier potential which is equals to 0. Right? Remember what is the barrier potential? Yes. So what is the barrier potential? The potential which is applied, otherwise which is available near the junction, which is termed as a barrier potential. Why the barrier potential is available? Near the barrier potential, the immobile ions are available. Because of that immobile ions, near the junction, some barrier is created. That barrier provides the potential because of immobile ions there. Okay, I am increasing my forward voltage again and again. So what will happen? The majority charge carriers which are getting recombined with the immobile ions available near the junction. That's why the barrier potential will become 0 in one particular time. After that particular time, after available of this, barrier potential is equals to 0. The electrons trying to cross the junction and gets absorbed by the positive terminal of the battery, right? That's why the current will be increased exponentially, right? So these are the things you should remember. Then only you can able to draw the VI characteristics of the forward bias junction. Okay, right? Right? So what is a forward bias? Positive terminal of the battery to P type, negative terminal of the battery to N type. So the depletion region width will be reduced because the majority charge carrier recombined with the immobile ions available near the junction. So once the barrier potential is equals to 0, at that time the electrons which is moving so fast and so much of accumulation from the N type to P type and gets absorbed by the positive terminal of the battery. That's why the current will be increased exponentially. Okay, so this is for the forward bias condition. So now we will see what will happen in the reverse bias condition. Okay, so already you know what is a reverse bias. So what is a reverse bias? The P-type semiconductor gets connected with the negative terminal of the battery and the N-type semiconductor gets connected with the positive terminal of the battery. Okay, now I am drawing that one. This is my P-type semiconductor and this is my N-type semiconductor. Okay, this is a junction. Okay, and consider this is the depletion region. So what is there in the depletion region? The ions will be there in the depletion region. Okay. So here it is a donor ion. Here it is a acceptor ion. Okay. So the electrons which are losing, right? The electrons are losing. That's why here the ions are the positive ions. So what ions? These ions. Okay, I want to make this a bit closer to this part, right? This is a depleted charge carriers. So there the charge carriers are depleted. Here the holes which are losing the positive charge, right? So what is the losing here? positive charge is losing here. So that's why here it becomes the acceptor ions. So it is a acceptor ions. So I am taking two columns, right? So two columns I am taking. These already you know, right? So here this also I want to make a bit closer. What is this one? This is your depletion region, right? So the depletion region with this much only. So this is the width of the depletion region, right? Okay, so the next thing, it is a p-type semiconductor. In the p-type semiconductor, what will be available? Holes will be available. So holes are the majority charge carriers. So I am making some holes there for your understanding, right? So holes are the majority charge carriers. Okay, and electrons are the minority charge carriers. So I will take some 3 or 4. Okay, in the n-type semiconductor, what is happening? Electrons are the majority charge carriers. See, electrons are the majority charge carriers. It is having more number of electrons, right? Okay, even it is having a holes, right? So holes are the minority charge carrier. Okay, clear? Yes. So now what kind of bias is this? It is a reverse bias, right? Okay, what is the reverse bias? Yes, what is the reverse bias? Reverse bias in the sense p-type gets connected with the negative terminal of the battery and n-type must connects with the positive terminal of the battery, right? So I am naming this voltage as VR because it is a reverse voltage. So this is a negative terminal of the battery and this is a positive terminal of the battery. Okay, again come to the working principle. Okay, see what is the applied voltage? Negative is a applied voltage. Where you are applying this negative voltage? To the p-type semiconductor. So what is this voltage? Positive voltage. So where you are applying this positive voltage? To the n-type semiconductor. Okay, see here holes which are the positively charged particle and the connection of that, the connectivity of the battery is a negative terminal. So means that unlike charges. So what will happen to the unlike charges? It will be attract. So what will happen? The majority charge carrier holes which are getting absorbed by the negative terminal of the battery because holes are the positively charged particle. The same will be happened at this place also. So what will happen? Here electrons are the negatively charged particle and majority charge carriers which is getting absorbed by the positive terminal of the battery. So all the electrons available here are getting absorbed by this positive terminal of the battery. See here which are actually losing? Holes are losing. So once the particular atom loses the holes, then what will happen? Negative ion will be produced. So what will happen? If this hole is getting absorbed, for example, this complete line is getting absorbed by this. This complete column getting absorbed by this negative terminal of the battery. So what will happen? These holes and all will become negative ions now. Earlier how many columns were there? 2 columns. Now how many columns were there? 3 columns. See, this complete column is getting absorbed by this positive terminal of the battery. So what will happen? It is actually losing the electron. So if it is losing the electron, then it will become positive ion. So what will happen? It will become the positive ion. See what happened? Earlier, this much only the width of the depletion region. But now, what is the width of the depletion region? Width of the depletion region is getting increased. So earlier in the forward bias, what happened? The width of the depletion region is decreased. But here, the width of the depletion region is increased while we are increasing the reverse bias. So how much reverse bias is increased? Those many number of holes is getting absorbed by this negative terminal of the battery, and those number of electrons will be getting absorbed by the positive terminal of the battery. So at the time, the depletion region width is getting increased. So here, width of the depletion region is getting increases because of the application of the reverse bias. Okay, right. So once the depletion region width is getting increased, so what will happen? See here, this is a junction. Okay, so one side of junction which is completely having a negative ion, one side of the junction which is completely having the positive ion. Okay, so here holes and all getting absorbed by this. So what will be remain? Only the minority charge carrier electron. Here all the majority charge carrier are getting absorbed by this. Then what will be left here? Only the holes. So what will be left here? Only the holes. See here, these are the positive ion and the available is also the holes. So what will happen? These holes can't able to get into this part. Here, these are the negative ions and the left is only the electrons. So these minority charge carrier also can't able to enter into this part and easily. So what will happen? These minority charge carrier trying to get absorbed by this positive ion and these minority charge carrier trying to get absorbed by this negative ion. So what is happening? This holes tries to reach to the depletion region. From the depletion region, it is getting absorbed by the negative ion. So these are the minority charge carrier electron which is getting into the depletion region. From the depletion region, it is getting absorbed by the positive ion. So which is actually moving now? Only the minority charge carriers are moving, right? So minority charge carriers current, already I said we used to call it as a drift current, otherwise we can call it as a reverse saturation current. So what we called it as a reverse saturation current, but the direction of reverse saturation current is opposite to the direction of majority charge carriers. I mean the diffusion current is moving in the forward direction, the reverse saturation current is moving in the backward direction. So remember, this is the direction of reverse saturation current and we have to denote by this letter IS. So I minimum, because of the drift current, it is a reverse saturation current and we have to represent it as a IS. Okay. So majority in the forward bias, majority charge carrier current which is flowing in the forward direction, this is for the forward bias. In the reverse bias, the minority current which is IS flowing in the direction opposite to the forward bias, otherwise majority current. Okay, right? So now all these holes are getting absorbed by this negative terminal, all these electrons are getting absorbed by the positive terminal. So what are all the minority carriers available here? Trying to get absorbed by the ions which is available in the depletion region. Okay, right? So if you want to get it as a diffusion current, the application of electric field is necessary, right? So if it is a drift current, there is no need of any electrical. See, this minority current which is happening because of the temperature, right? So I minimum, the reverse saturation current which is happening because of the temperature. But if it is a majority current, it has happened because of the application of electrical field. If it is a drift current, that has happened because of the temperature. Okay. So, if it is a reverse bias, you should remember how should be the connectivity and what is happening to the majority charge carrier and what is happening to the minority charge carrier and why we called it as a reverse saturation current. Okay. So by this class, we studied what is a forward bias and what is a reverse bias as well as the working principle of forward bias and reverse bias. By next class, we will see how to draw the volt ampere characteristics of the forward bias and reverse bias PN junction diode. We used to call it as a VI characteristics. By next class, we will study about this. I hope you can understand everything well. Please go through the video. If you have any doubts, please post it in the comment box. Thank you so much.